Welcome everyone. This is Joe Armstrong and the Power Systems Virtual User Group webinar. And just want to let you all know that I am recording this session. And not sure, probably not saying anything, so you won't be on it, but the replay will be there. So a couple of things. First of all, I have one announcement. If you're not aware, actually this is, believe it or not, the 35th this year, 2021, the 35th anniversary for AIX. So yeah, I remember we did a big one for IBMI a bit ago. So this is for AIX. So a couple of things are going to be happening later in the year. So not yet and nothing today necessarily, but a couple of things are going to be happening. We announced, IBM announced a statement of direction for AIX 7.3. So one more tickie that AIX has got a future ahead of it still, which I hope that we've kind of been able to get across to the community here. A lot of future left in AIX. So 7.3 is coming, and IBM's announced that. No details yet, but a little heads up here. Next month for the March webinar, I'm going to have the AIX offering manager and Carl Burnett, who's in one of the leads for the technical part of AIX, and they're going to be giving us a little bit of insight into what's coming, and also talk about some other things around it and some other announcements. You know, we talked about Ansible and some other things, so we're going to be talking about that next month. Be sure to join us and learn what's coming, and then as the year rolls on, there's a huge announcement that we're going to do when we start doing the GA of 7.3, and I'll cover that, and we'll have more details. All right, so there you go. But today we're going to continue the January session where Earl Jew and Tom Prokop talked about tuning, and we did a pretty deep dive into AIX and some tuning stuff. And today, Earl's going to talk about something that we've covered here, but not for a long time. And Earl talks about tuning by the numbers, where he shows us different numbers in the system, and not necessarily, you know, this is a 3, so it means this, but more like this has 5 digits versus 2 digits, and that means something's wrong or something's right or whatever. So Earl's going to talk about that. And go a little bit about tuning, and this is a great session. Lots of good, really useful information here. The presentation materials are on the wiki site, actually in the January session, because I posted both months. So if you go into the wiki, the presentation materials are there, but look in the January section. And then one other thing before we start is that if you're going to ask questions, please put them in the Q&A pane, not the chat pane. Feel free to chat away in the chat pane all you want, but if you have questions, we'll monitor the Q&A pane for those. Okay, so if you weren't here last month, Earl is with Lab Services. He is a tuning guru, has been doing it, I think, since I started, along with other things, doing this job a lot of years ago, and has just got an immense amount of knowledge in the depth of AIX, what happens deep in the system, how things are affected and what they mean, and a lot of experience that he's put together in these presentations and is willing to share with us. So Earl's going to be our main speaker. We've also got Tom Prokop. Tom is a colleague of mine, a mentor of mine when I first started doing this 14 years ago. So he's even, as he says, older than dirt. Tom's going to be kind of, you know, answering questions and chiming in a bit as well. So we've got both of them. We're very honored for that. So with that, I'm going to turn it over to you guys.
Thank you, Joe. This is Earl. We have another session in between called Mapping. That one you can read on your own. It's a little too deep for the VUG. Sorry, I offered it up. It's for people with the bigger propellers. I thought this would be more tactical and more immediately useful. I have 90 minutes here. This is usually designed for a 60-minute presentation, so hopefully we'll have a better real-time interaction for Q&A through the Q&A window. So evaluating the cumulative statistics, these are all the numbers that most of them grow over time. Hopefully you can see my cursor this time.
Yeah, it's a little black cursor there.
A little black cursor only when I move.
Shows up a little bit better here.
Yeah, well, it didn't exist last time because I chose the wrong mode of presentation. We're talking, this is a more advanced session. It's very tactical. I lay down rules for what these numbers mean and what's high and what's low. I do not offer much at all in the way of resolution for these issues. Instead, when it comes to performance tuning, identifying the issue is the greater need versus how to fix it. Once you know what's wrong, it's generally pretty easy to know how to fix it, okay? This is the 5th of a series of 6 sessions. I presented tactical dissection January, and the essence of this first one was presented, I believe, in 2019 when I was, I think that's what, so what's in here you'll see in a previous recording. This mapping, you have it, I'm just not speaking to it, it's too deep, and now we're here, okay? What to know? All of this regards the numbers of VMstat-SV, the cumulative stats. We're going to go, everything's adapted to uptime, how many days and hours and minutes, because these numbers are growing over time. -S, cumulative counts of AIX events, -V, changing percentage in counts, which go up and down, and then the cumulative blocks. So that's the structure of this. This is -S. Those are the days uptime. And this particular LPAR called EDDRD is an E980, SMTA, shared processor LPAR, SPLPAR, shared processor LPAR versus a dedicated CPU boot. Note that this uptime is 1 day and almost 21 hours. A very significant load average. This load average. 195.6, the load average of the most recent 1 minute. Load average 334, the load average of the most recent 5 minutes. And 394.69 is the load average of the most recent 15 minutes. Load average is the load average of threads on the run queue. The VMstat, KTHR, R run queue. This is the workload, and this is very substantial at 3 digits. Most of us will not see a sustained 3 digits ranging up to 400. This is a big LPAR. I bring this up because the day's uptime here is only, like I said, 1 day, 21 hours. You don't know it, but for this short time, these numbers are huge. We're going to go through this organization of colored blocks for -S. These are cumulative counts. And the rationale behind all these numbers is essentially not documented anywhere in any red book or any resource I have found. So all that you're going to hear is from my field experience only. This is -V. This you should be more familiar with. These numbers are huge and growing. The data for this LPAR hasn't fully loaded in just these less than 2 days. So that's why there's so much free memory. Anyways, we're going to go through these and this organization are colored blocks. Important. Generally, the greater the day's uptime, the bigger these numbers grow. Okay? Because these numbers only ever grow. And what I offer is a tactic to understand if these numbers are big, small, normal, outstanding, or not at all. When I first started in 2002 with this passion, I would ask my masters, what's this number mean? And they would say, oh, if that number is too big, do this. I'm like, okay, great. How do I know what number's too big? Dead silence. How do I know if that number's too big or too small? I said, I don't know. If it's too big, just do this. Oh, geez. I had to come up with some formulaic reference just for myself when I'm working. And after I went through literally thousands of these script runs, analysis for performance, you begin to get a sense of what's high and low and what to expect. And not only that, you discern what the meaning of the numbers are. These cumulative counts, though, they each grow at a different rate across the day's uptime. Okay? They don't all grow at the same rate. Some grow bigger, faster, and others grow slower. And thus, across more days uptime, their comparative differences grow wider. Okay? The speed of light versus the crawling of a snail. At 1 second, the distance is not that great compared to 2 years. Then the distance between the snail and the speed of light is huge, okay? So this is what I mean by the comparative differences over time. When I meet an LPAR with a 3-year uptime, boy, the numbers are huge, but also they vary greatly versus 5 minutes uptime since boot, okay? So this is why I've had to evaluate these numbers at a standard of 90 days uptime. Now, 90 days uptime, utterly arbitrary. But I found that 90 days works as a good standard as a multiple of typical uptime. If your uptime is 10 days or less, you won't see much differences in these numbers to a 90-degree standard. If your uptime is 2 years, you have to adjust a little bit for the fact that it's so long. So 90 days uptime, it turns out for me a convenient multiple for this standard uptime. And we only regard the digit counts of the comparative ranges, proportions, and ratios. The digit count is enough to distinguish the character of these numbers. I know this just from experience. I have no white paper or anything to offer you to back up my words here. Please believe that this tactical practice is sufficient because there are vast and exponential differences of character in the AIX processing workloads. The differences in the numbers are highly characteristic. You just have to begin to practice looking at them, and you begin to realize that our workloads are all not processing in the same way at all. These differences are almost always exponentially definitive, distinctive, and the digit count makes it good enough. You don't go into exact numbers, you just count the digits. So we standardize it on 90 days uptime. If your uptime is 180 days, multiply by 2. If your uptime is 45 days, you divide by 2. If your uptime is 88 days, close enough. Tom, anything to add on that?
Yeah, there's always a time series aspect of this. There's the intensity of the workload over time, 90 days, for example. But there are often workloads that have very intense periods during a day. And so you might see these numbers where they might not actually look like they're an issue, but you might also want to dig into, gee, this workload runs for 4 hours in the middle of the night or just during a couple hours of the day on, say, a business cycle. Say it's an end of the quarter, end of the month type workload, and the rest of the time it's not doing anything. So I always color this with these numbers need to be examined when the workload is running, and if the workload is running intensely only for short periods of that 90 days, you need to refine your examination to those periods when it's running intensely.
Yes, totally agree. Perf PMR by standard collects standard of 600 seconds. It dives into the real-time 600-second collective workload, cumulative workload, very deeply. This is a perspective apart from real-time. Of course, I have a whole slew of presentations on real-time monitoring. But this is a unique perspective in that it is not the perspective of Perf PMR, it's cumulative. I have customers that write a script that do the math of differences day to day on these numbers. I don't have that kind of data or access, but they can. And on the math of differences day to day, they begin to lay down standards of expectation.
And so the difference is, capacity planning and performance look at most of the same numbers, okay? Performance, as Earl said, is more real time. When the workload is hot, what is it doing in the system? And capacity is obviously the long-term trends. What is it doing over a longer period of time to make sure that we have enough capacity in the system? Don't confuse statistics collected from a capacity horizon with those collected for analyzing performance, even if they're the same the same values or the same metric that you're looking at. They mean different things because of what
Yeah, I don't get much into capacity planning because we have such wonderful tools out there for it already. You know, NMON, LPAR to RD, all of those tools are capacity management review. What I try to do is I try to do analysis and tactics as the technology advances from Power 4, 5, 6, 7, 8, 9, 10, 11, okay? So every time we come out with another power generation, I have to rewrite my curriculum in adjustment to that technology. Okay, there's a big jump between Power 4 and Power 5, remember. So let's start off here with -S. This analysis is and offerings is purely from me. There's no reference I can offer. Nobody writes about this. This is a big LPAR. SMT8 shared, 48, half a terabyte of RAM. But note, 96 cores in the system, only 60 are licensed. That means they're lighted, they're active. That means 36 cores are dark but available upon capacity upgrade on demand. So this is a perspective that we often miss. How many cores are there and how many are actually licensed? The count of how many are licensed means you may think you have 96, and you do, but only have access to 60. That's a big difference. Okay, this subset was about the total scale of virtual memory used and what purpose it was used for. Okay, very important set. Start off with the first number. AGIS translation faults. This is the scale of how much memory from AIX, virtual memory effective memory addresses, are mapped to real memory on DIMMs. This is the conversion of virtual memory to real memory. This number has been growing and growing since 2002 and Power 4, even earlier, because our use of memory and the amount of I/O that we can do all needs a home on physical memory. So whenever AIX needs memory to create a process, all processes you create are new. I shouldn't have used the word new there because you never create an old process. So all processes have AGIS translation faults. And every time you read data through free memory and the JFS2 cache, you have AGIS translation faults. That's new data going through free memory and the cache. You have to allocate virtual addresses to DIMMs for the standard traditional I/O, as well as writes. When you're writing data from the process to free memory to cache to the SAN, you have AGIS translation faults. There is a proportion of AGIS translation faults. It's not one-to-one. But even though it is done on ranges, it is still indicative of scale. Now, this number is growing huge. In general, the bigger is that number, the bigger your LPAR you need if you want performance. If you don't have a big LPAR for that big number, the workload still runs. It just has more struggling to do, but the workload will run, which is why this concept was never introduced. I've written a presentation, must be 4 or 5 years ago, about assumed scale of design. I am now writing my 2021 curriculum, and I'm going to come back to assumed scale of design concepts, in that we need to recognize that AIX runs on 4 gigabytes of RAM, all the way out there beyond 4 terabytes of RAM, and yet no one has written about what happens across this expansion of scale and how to attend it. I will try and write that for my 2021 curriculum. AGIS translation faults. It's how AIX maps virtual to real on the architecture. Virtual addresses, effective addresses at our level of speaking is the same. In other words, AIX thinks in virtual, the hardware thinks in real, and we have a map of pointers in between. This is an essential workload of the hypervisor to map what you have in virtual addresses to real addresses, and we have page table entries, which are the pointers from virtual to real, in the translation look-aside buffer and the hardware page table. It is the map of your AIX addresses to the real world on DIMMs. Again, this is a major essential workload, or essential function of workload, of the hypervisor and the hardware. That all underlies the great invention of virtual memory. AIX translation faults. Count and scale of memory used for making processes and managing VMM-initiated I/O and buffers and all the rest of it, okay? So this is what I call making it real. In my 2021 curriculum, I offer an in-depth review of concurrency and AIX translation faults, ERAT. Effective to real AIX translation is ERAT, ERAT. And I have that presentation in my 2020 curriculum. It probably ran too deep again, sorry. Okay, so that is AIX translation faults, and that number really means a lot. Remember, this session is called Cumulative Stats to Evolve Capacity Planning. Okay, so we're talking about these AIX translation faults. And from my experience observing this number, if you see 9 digits in 90 days, you hardly have a workload. 10 digits, it's light. So this is a digit count. Now, 9 digits, 10 digits are very small numbers compared to 11 and 12 digits. Most of us with a workload that matters will be 11 digits at 90 days. Mind you, an 11-digit number is a very vast range of numbers, okay? Most of us are going to fall in that 11 digits. Well, you look at here, this is 10 digits at almost 2 days. You multiply this by 45, and we're in the 12-digit range. When I first saw this LPAR, when they sent this to me, I looked at that and went, oh, that's not much of work, until I noticed it was less than 2 days. And I went, oh my gosh, this is huge. 12 digits, it's a rare, frequently large AIX memory demand. I've seen less than 200 of these cases since 2002. 13 digits is a massive scale within 90 days or at 90 days uptime. It's the scale not unlike Apple Computers, iTunes America. I've only seen 2 cases at this range. One of them was the post office of an entire continent, okay? So if you think of all the shipping and packages, data of an entire continent of a post office, that's the scale of 13 digits. 14 digits, I don't think we can do it yet. At least if I don't see it, I can't claim that it can, okay? So this is scale of memory used. It's a digit count of everything made real for processes and data. The reason why this concept is important is no capacity management tool uses this. It is a wonderful comparative scale of memory use. What I mean by comparative is if you watch this number on one LPAR and its workload that you know very well, you can look at another LPAR at same similar days uptime and realize, wow, this one uses a lot more memory than another. The other reason why this concept is so important is, this is a big one. Most of us are worried about having enough CPU, which is traditional and long-time worry in the IT culture. Today, our CPUs and how many we typically configure are often too many, and we are challenged to use those CPUs. We are not getting and deriving all that a CPU can produce for us. We are challenged to make them busy. It's no longer available as CPU time that matters as much as it used to. It is more about how well you feed those CPUs. We all understand this adage. A CPU will only execute processes and data that you give it to do. Most of the time, and I'll prove this in my 2021 curriculum, most of the time our CPUs are spinning and screaming for work that never arrives. This perspective is because of the advances of technology. We are more challenged to feed workload to our cores than our cores has an ability to execute. That's a huge strategic statement. And in all of the hardware advances from Power 4 onto what I'm watching right now, Power 11, it isn't about executing threads faster. It's more about advances in feeding instructions and data to the cores so that the cores have something to do. It's kind of weird, but that's what we're doing in all of our advances between power generation. Bigger L3 cache, more aggressive prefetch, greater depth of concurrency, the number of things we do at the same time. That's what I do. I try to adapt performance tuning to what the technology does. And every generation of power takes a major shift. Okay? Tom, anything to add on that?
No, you hit the nail on the head. I mean, a lot of folks focus on, gee, how fast is the core in gigahertz and all that sort of stuff. And the real key is cores consume instructions and data. And if you can't feed them well, they have nothing to do. And that feeding them well is both a hardware statement and, in some cases, an application design. If you have an old piece of code, say circa 2005, and it ran great back on SMT2, for example, you move that into a modern processor, it's going to run SMT2 threads just like it did back then. It's not going to be able to spin up enough workload to keep these modern processors fed with things to do. So behind the scenes here is not just keeping up on the hardware, but keeping up on the software stacks. You know, software designers and application developers, they're always looking for how to run more work, get more things done, and that comes with newer versions of software as well. So that's another kind of hidden message here that, yeah, we can move that 2002, 2004 workload. We've got AIX binary compatibility, and it'll run great, but you won't be taking advantage of the new features and capabilities of the system. So we encourage people to move to newer versions of code wherever possible so that they can get the best value out of the newer systems that they're putting in place.
Yeah, that's a culture of change, rapid evolutionary change. Page-ins and page-outs. These are the traditional JFS, JFS2 reads, rereads, and writes, rewrites. And most of our applications that have exploited our technology don't use these methods. Instead, they use these direct I/O methods, CIO, raw ASM, and of course MMFS, which is GPFS, which is spectrum scale. I don't know what they call it today. Direct I/O methods don't use free memory, don't use the cache, and software adapted to exploit direct I/O methods skip over the traditional AIX overhead that I'm explaining here. So reads and rereads through free memory to the cache. We understand a read. What's a reread? A reread is you read the data into the cache, you use it, and you throw it out to make room, make free memory. And then you have to read that same piece of data back in again. And you throw it out and reread it back in again and throw it out. What about reading it and keeping it? Isn't that better? So having enough memory in this regard reduces rereads. And that rereads is not a concept of tuning, but I have to deal with it. I have to see it. How do you know if you have enough memory for all the data to reduce rereads? Rewrites, you can't avoid it because you're writing the data, right, to preserve the data on SAN storage. So reads and writes and rewrites, concept that's non-traditional, but we have to deal with it. You see, if you don't have enough memory in general, not a profound shortfall, but if you don't have enough memory, your workload will run. But reducing workload that you can avoid is a new principle of tuning. It is what I govern my tactics by. What? What I do with tuning is beyond sufficiency of entitlement in virtual CPUs and memory. What I do with tuning and what I care to teach in this next year's curriculum is how to avoid avoidable workload. Not doing something slow and unnecessary is always faster than doing something slow and unnecessary. And in order to decipher how to remove avoidable workload, you need to kind of understand the hardware, the hypervisor, what AIX is trying to do, and what is your workload trying to do. This is what makes tuning so special for me, but also very, very mysterious for everyone else. So if you're using direct I/O methods, you won't have these issues. Because today, our storage is no longer, if you buy the right stuff, it's no longer spinning. It's solid state flash stuff, right? I don't need to worry about tracks and rotational delay and head seek and all that anymore. It is so fast today that this part of what I'm describing of traditional AIX is being skipped over. Given the speed and efficiencies of today's SAN storage, if your application can support a direct I/O method, please use it. It skips over all of this intense traditional JFS, JFS2 stack, and JFS2 cache use. This is a big deal, especially given that our storage is so much faster. Back in the days when this was originated, we were still on direct attached SCSI disk arrays. I mean, fiber channel was just emerging as a standard back then. The latencies of SCSI direct attached disk arrays on SCSI cables that must be less than 2 meters long, if anybody cares, is what this was all built to accommodate back then. Storage doesn't spin anymore. So the latencies added by this overhead relative to the responses of storage is a very different proportion of overall latencies. Tom, you want to spin something into that?
No, I think that's a good summary.
Page-ins, page-outs, old traditional. Paging space page-ins, insignificant for performance. Why? Because their latencies of a paging space page-in is not unlike reading data. Now, look at the number, okay, to see how much is coming in after it goes out. But if you never paging space page out, you will never paging space page in. Well, this LPAR has 55% free memory. It's not going to run out of memory, at least right now at the moment. Right? Paging space page outs, in grave contrast, is the most critical memory performance indicator. Now, they should not exist in today's reality of our technology, but if you have them, they are not an error. Back when I was young, skinny, with more hair, paging space page outs was a way of life. We never had enough memory. So the OS is built to accommodate them. They're not an error. They're just not good for performance. And as I say here, it's the slowest, harshest method for releasing free memory. You don't want to make free memory by paging space page outs. So first thing I look for is paging space page outs, because if you got them, something ugly happened since boot. Now, Of course, it matters how many you have. That count is the count of memory over commitment, whereby the memory of the executing workload, all process, plus the memory of shared memory was growing bigger than the amount of physical memory the LPAR was configured with. That's what's called memory over commitment. Right? So this count, really critical. You don't want any of those to occur. So I have my free memory rule number 1. 5 digits at 90 days is acceptable tolerance. That means if you've got 5 digits at 90 days, you got a problem, but it's not a major one. It's acceptable. It used to be, not that many years ago, that when AIX booted, all by its lonesome, it somehow accumulated 5 digits. So I always threw away the first 5 digits because I don't know why. Back then it just did it, but it doesn't do that anymore. Each digit beyond 5 digits exponentially increases priority resolve, meaning if you see yourself at 6 digits at 5 days, you're already blew it, right? If you're 6 digits at 90 days, yeah, you've got some concern, go find out what it is. If you're 9 digits at 90 days, yeah, you got a real problem. That's really a profound problem. So this is the first rule. Zero-filled page faults. This is memory used to create private processes and shared memory, okay? What we do is you allocate memory and you fill it up with zeros so that when you write the process, you just write the ones. That's why it's called zero-filled page faults. This is memory for creating processes, shared memory, and of course, dynamically spawned buffers of AIX, right? Zero-filled page faults is can be a substantial proportion of overall address translation faults. Reference, about 33%, like you see here. Okay? So all processes are created once, never recreated, and they're always unique allocations of memory because you create a process only once. The reason why it's a major proportion of address translation faults is because most user applications are comprised of multiple similar processes sharing the same code. Today, we are a reality of clones. This is a good thing. It's not a criticism. When you have many similar processes running exactly the same executable code, I call them clones. Now, that's not documented anywhere except me and my poetry. But a clone process is getting to be what we find on most workloads today. Many processes running and built exactly the same way in size, just processing different data. This is a good deal to know, because if your workload is primarily consisted of clones, you have a very uniform pattern of execution. And thus your tuning will hit on that, enhancing that pattern of execution a lot better, a lot harder, a lot more confidently, as I say. Executable filled page faults is the executable code. This is what's used to create the process as well as what the process is executing. And all clones share exactly the same copy of executable code instructions. Okay? So you read in that code once, this executable page faults, they come in as data. Once they create the first process, these pages convert to computational memory, and their executable filled page faults stay in memory until next reboot. So they come in as data, convert to computational memory, and stay there forever. So all subsequent processes run exactly the same single image of code. Executable code, executable filled page faults, same thing. And I've concocted, as I usually do, I make things up, but back it up with reality, okay? Clonedness, another concocted concept. Clonedness, what is the degree of uniformity of all processes? It's a secondary indicator. It's my confidence factor, okay? You divide zero-field page faults over executable page faults, and you get a ratio. In this workload entered, it is extremely high clonedness ratio of 30,000 to 1, if you just do the math. Not unlike TSM. TSM might be up 5 years and you only see 5 digits of code and trillions of processes over and over again, okay? So this amount of code versus how many zero-field page faults is the clonedness ratio. I use it, I don't know. You sometimes will see executable page faults ranges out to 10 digits, even 11 digits. Telling me that you got a whole lot of code and likely you have a lot of different categories, classes of clone processes, which is a very different workload versus this. I presented this so many years ago and again. Tom, is this useful for anybody? Or is it just me again?
I think it's useful. I mean, understanding that, you know, for example, if I'm looking at I'll use a database as an example, and I'm seeing a real high executable filled page fault relative to 0, I may have something going on in there where I'm creating lots of connections, and maybe I'm not using connection pooling. So it's kind of an indication of what is the workload actually doing? Is it continually creating new processes all the time that need new pieces of code and new memory? And that's not very efficient if you can get away from it. So it gives you an indication that there's something you might want to go investigate relative to how the workload is creating processes and for what reason it's doing so. And if you can, you know, eliminate that or reduce it, your workload will run faster.
This is the main reason, these executable page faults, where you should never mount your binary directory, executable binary directories, with the concurrent I/O option. Because you throw out these instructions from computational memory because they're mounted in that fashion. It really slows the workload down when every time you create a process, you have to go hit the sand to bring those instructions in before you create the process. So binaries, binary directories, you know, don't mix your data in with your binary directories, please, right? I mean, it really matters. Don't mount them CIO. I mean, I've had several cases across these decades where, you know, customer unfortunately mounted their binary executable on an Oracle bin directory with the concurrent I/O option, and it they hurt themselves. So, you know, understand what these options do. Okay, that's the whole thing. Jeff, thank you for your comments there. This subset, it's all about LRUD, least recently used daemon. This process was the bane of my existence way back at Power 5. LRUD, extremely high priority daemon that typically scans memory pools for least recently used file cache pages to release as freed memory. Now, this is extremely high priority. Back in the day when memory was slim, this here got priority 17. It still is priority 17. Okay? You see, I'm talking about memory pools. We're going to get into memory pools because they really matter today. The count of memory pools, the amount of free memory is listed with -V. That's the next section below. But let's just talk about memory pools now. Don't worry about it. We'll get into memory pools. Okay? So that's all about LRUD. Every memory pool has a clock hand. This clock hand spins round and round. Today, we are list-based. We actually have 2 lists which LRUD points to. One list is just file cache pages. Another list is just computational memory pages. And when we go revolutions of the clock hand, we're just spinning on the file cache pages list of memory per memory pool. Now, the words didn't change since it used to be that LRUD scanned the entire memory pool, whether it was computational memory or file cache pages, but the definition changed, okay? So this is scanning your file cache pages round and round in revolutions. And every clock hand is a TID of LRUD, meaning if you have 6 memory pools, you have 6 TIDs as clock hands in LRUD plus 1 master thread in LRUD. The more memory pools you have, the more clock hand TIDs you have inside of the LRUD process. What traditionally used to happen was that large LPARs with many memory pools scanning and freeing LRUD all the time for lack of free memory and always making free memory along large LPARs. LRUD was a major component of the kernel workload. In those days, the kernel workload was oftentimes greater than the user workload. Okay? Hopefully you don't have that today, but at least you can see what these numbers mean. Pages examined is scanning cumulative real-time. Real-time, VMstat, false, SR, scan rate, but this cumulative, and then a page is freed by the clock. Never, unless there was an error in AIX, and there used to be, you will never free more memory than you scan. It's always a scan and you free a subset. First time I saw that it was freeing more than it scanned, I complained. And they told me, we'll fix it. But Earl, you're the only one who even looks at this and notices. Yeah, okay. You scan more than you free. This matters. This matters a lot, okay? And then this here is the revolution of clock hands across all memory pools. Not just one, all of them. Now, originally, AIX had only one memory pool when the world was small. Now we have multiple memory pools. So these counts matter. Here come the rules. Here comes why it matters. After watching these numbers for so long, I've come to realize that, as a rule that I've been tuning by, your pages free should be greater than 40% of all pages examined. Or more simply, pages free greater than 40% of pages examined. Yeah, consider it arbitrary, but that's what you're here to learn from me. What do I do? How do I do it, right? And here's why it matters. If you scan a lot and free a little bit, you have a whole lot of kernel overhead scanning and not making much free memory. Time to add memory, because your data is too much bigger than the RAM of the LPAR. When I say data, I mean the access data. I mean the data you read in a day. If you're reading in 4 gigabytes of data or writing 4 gigabytes of data in a day, and you have 100 gigabytes of RAM, hey, that all fits real sweet. But if you're reading and writing a terabyte of data in a day and you have 4 gigabytes of memory, it will run, but it's going to struggle because there's too much data versus how much memory you've got. So this here is how I gauge, hey, your data is too big, you're struggling too hard to make free memory given the scale of your data, and this problem grows worse unless your software application is using concurrent I/O, ASM, GPFS, or RAW. Okay? That's why I'm writing this. Now, here the numbers are weird. because this only booted less than 2 days ago, I can't see why there is any LRUD here. So I had to put in the qualifier that after 10 days, or at 10 days, these numbers become valid. You've got that strange, weird period of boot up where things just don't make sense in the first 10 days or so. So, you know, the rule doesn't apply here. Unfortunately, I have to make this exception because of a poor choice of LPAR. But I need to point out that this is a cumulative review, the overall workload. Right? So we got a rule. The worst I've seen is that only 2% of all memory scanned was freed. That's terrible. Well, let's think about what that means. This is a least recently used daemon, meaning if the data is fresh, it was very recently used, don't steal it for free memory. If you scan a lot and free a little bit, it means all of your data is fresh and new. If you scan a lot and you free most of it, all of your data is least recently used, meaning it was easy to free. That's why these two numbers matter. That's why I have this rule. Those of you lucky enough to use concurrent I/O, raw I/O, GPFS, or ASM, you don't have these issues. It's just generally that legacy stuff or software that hasn't adapted to exploit the technology that has this issue. Rule number 2 is below. What about revolution of the clock hand? You know, the total scans of all of your memory pools. There's a rule here too. This LPAR is huge, half a terabyte of RAM. It shouldn't have any revolution of the clock hand at all. But I have to throw this data out here too. It's not quite 10 days yet. The worst I've seen, for your reference, is 66,000 revolutions of a clock hand per day. That means all of your memory pools are scanning like crazy, trying to make free memory. Well, that's an indication to me that the amount of data that you're trying to read in doesn't have enough memory to hold it. So it's just screaming and screaming, trying to make free memory. The workload runs. The workload runs. AIX is performing as expected, as designed. But you can't find out why it's running so slowly. That's where I'm going. Yes, Tom?
Let's put that in context here.
Okay.
So when LRUD is scanning, tell our colleagues, what is your workload doing when LRUD is scanning for free memory? And your silence is perfect because that's exactly what your workload is doing, nothing. It's waiting for the memory so that it can do something, either execute an I/O or execute an instruction. It doesn't have the memory it needs to go to the next step. It requested memory, and it's waiting for LRUD to find memory so that it can then translate a virtual address, which is all the workload knows about, into a real piece of memory where an instruction or a piece of data can be lodged that the workload can then use. So when LRUD is cranking away 66,000 per day, your workload is not progressing. You've got a great LRUD system. That's all you've got.
Yeah. I mean, I've had customers come to me and said, my processes are running too slow. And I'm saying, no, they're not. Your processes don't exist to run. Huh? If you don't have free memory to create a process, is it hard to believe that process can't execute? Well, yeah, they understood that. Processes only can execute if you have memory to create them. So if you don't have enough free memory to create them, they don't run. So once we up the free memory, far beyond default, by the way, yeah, processes get created faster and they run better because they exist. So that's the total revolutions of the clock hand, meaning, in general, how long does data stay in cache? Revolution of the clock hand should be less than the day's uptime as a reference. You see, if you have revolution of the clock hand equal to the day's uptime, 4 to 4, say, it means in general your data remains in cache about 24 hours. If you have 2 revolutions of clock hand per day, then your data in general is in cache about 12 hours. If you have 66,000 revolutions of clock hand in a day, your data in cache doesn't get to stay there very long and gets to be reread and reread and reread, or again and again. I mean, it's a real problem. Is it a fault of AIX? No. And that's why this kind of thing is often overlooked. Maybe not anymore, but it's often overlooked by support because there's nothing broken. It's running exactly the workload you gave it to do. Of course, when you ask me to look at it, I have a coronary. And I get to fixing it. This is the difference between tuning and the wonderful, helpful people of support, because those guys teach me things all the time. Free memory rule number 4, revolutions of clock hand greater than days uptime is an indicated performance issue. I don't mean 1 digit, I'm not talking about, I'm talking about orders of magnitude greater than the days uptime. You know, like I often see them, 5 digits of revolutions of clock hand in 10 days, in 20 days, and I'm like, wow, okay. It's not broken. It is more that you need to do something about it. Like I said, I'm going to identify issues. Fixing them is easy. You just add memory. Backtracks. No user performance that I can uncover. If you can uncover some use for backtracks, please teach me, because I'm open to learning from anybody. Okay? Free frame weight. Yes.
So at some point when you get to a breaking spot, let's kind of go through some of the questions and some stuff that Tom has pulled up as well.
Sure. This is a critical piece, but this will wait. What questions do we have? Because I'm not watching you guys. I'm sorry.
No, that's good. That's good. You shouldn't have to. So there were some questions around the cloudedness that you brought up.
Cloudedness.
Yeah, the new thing. And you talked about you showed the example of the 30 decay, and that was high. There were some questions about what's not high, what's not too high, and what's like, 135 to 1. Somebody said, it's 135 to 1. How bad is that?
It's not that it's bad. And the higher is the clonidry ratio, the luckier you ought to feel. It's not that it's bad or it's good. It is the character of workload that you're running with. If you're like 100 to 1 or 200 to 1, it means you have a lot of processes that are likely running and are created on different code. That means you have a variety of processes all doing different things with the same data, which is very different from many processes all doing the same thing on different data. So it's not good, it's not bad, it just turns out that's the kind of software you're running. I had one customer who had a non-production LPAR, and their executable page faults was greater than zero-filled page faults, and I said, what the heck is this LPAR doing? Oh, we use it for testing databases and DataStage and Java and WebSphere, and we never reboot. We just test all of our software here. And I'm like, oh, well, gosh, no wonder. And no wonder executable page faults is so great, because they're running a variety of applications on the LPAR without rebooting. So it's not good, it's not bad, it's the character of what you're running. I think I just saw my nightmare flash up talking about AME.
Yeah, did you see that question? Is any of the numbers in VM-stat-S affected by enabling or disabling AME?
Yeah! Big time! AME completely scrambles everything I teach. When you activate AME, it's a whole entirely different practice of monitoring and tuning that I just don't get exposure enough to do, so I don't attend it. Not many people use AME today. AME is great for non-production LPARs, but when performance matters, there are only very rare cases where you'd want to implement it in performance priority workloads. AME is a completely different avenue of practice, and I don't have enough exposure to lay down those practices. Other than to state, AME is perfect for non-production workloads, you know, your red-haired stepchildren workloads. AME skews my numbers, and I don't want to teach what I can't prove. I don't want to teach what I'm only guessing at. Call it a cop-out, fine, but
Good enough. Good enough.
Yeah, so AME is becoming more viable, definitely with Power 9 at Power 9 mode, right? You know, because we're now allowing compression, decompression using our hardware accelerator of 64K pages. That's huge. That's huge. I just don't have enough exposure to lay down practices.
Yeah, and Tom here, I would concur. I see a lot of clients deploying AME in a non-production workload. It's not so much a red-headed stepchild, but you've got a lot of workload on systems where you're mixing production and non-production. And perhaps, but not in all cases, but perhaps those workloads are not busy all the time, and they don't really have service level agreement performance targets. And so you can squeeze their memory by compressing it and get more non-production workloads into the frame. Similar to what we do by analogy, where we under-entitle workloads that are not important, put them in a shared processor pool, give them a quarter core, 1 1/4 cores on maybe 4 or 6 or 8 virtuals, and we know they're not going to run great, but that doesn't matter. We're sharing the CPUs. We're not sharing memory with AME, but we're kind of doing the same thing. We're squeezing workload into fewer real resources because it doesn't need them all the time. But for things that matter, performance, critical business workloads, things that are really important in that sense, AME is typically not deployed because it, by its nature, is going to potentially impact performance for those workloads. Again, non-production workloads are a great place to go look at AME. I wouldn't recommend it without a lot of thought and examination on a production workload.
Tom, is AME still an added feature that costs?
Yes. It's
okay,
an extra feature for the hardware.
The hardware, okay. What drove me nuts, Tom, is I found AME overlaying active memory sharing, overlaying active memory dedupe, and I just lost my mind. I didn't know what to do with that one.
That's too many layers of complexity. I don't know if I can.
Yeah, and I just can't play there. My advice to them, if for their inconsistent performances, don't do it. Okay. It's not that it isn't viable. It works. It's great technology and right application. I just can't lay practices for it. Okay.
You know, all of our virtualization technologies, you know, are shared adapter technologies through VIO, and there's multiple ways of doing that. Our shared processor pools, our dedupe and memory sharing features, and AME, all of those have trade-offs. And it's a simple matter of understanding what are your objectives with the workload, and what are the trade-offs if you use some of these sharing technologies, and what's the impact on your objectives, performance, throughput, et cetera, for that particular workload from a business perspective as well as managing the workload. They're all great technologies, but there's places where they fit really well, and there's situations where they don't fit really well. And it's a simple, examination of, does this technology give me a benefit relative to the trade-offs that that fits within my objectives from a business perspective. They're great technologies. They work really well.
They are great technologies, definitely, and very innovative. This is,
Hey, Joe, I think this would be a time for me to bring up that one chart. If you're okay,
yeah, go ahead,
I've got
share.
a chart
I'll
from
get out of here. You want to share something?
I've got a chart from a presentation,
hang on.
or actually a document. I'll continue talking while you let me share. That
Okay. There you go, Tom.
All right. Okay. Make sure you can see this.
Yes, I can see it.
Good. So, Earl, this chart, this graphic, I think, pulls together a lot of what we've been talking about with what's using memory, particularly your conversation about file system memory. Where does this go? Where does an I/O go that the application issues when we're using file systems versus raw disks, which would be concurrent or direct I/O? So maybe just kind of walking people through this a little bit would kind of tie things together, and I like a picture says 1,000 words type thing.
Yeah. You see J2 dynamic buffer pre-allocation, that regards to on-demand addition of JFS buffs, right? When you exhaust the buffers on a given file system, we make more of them from free memory, and we release them back to free memory when they're not used. So, I'll get into that, but the default of 16 means make 16 more FS buffs when you exhaust the FF application we've got, and make them for free memory. We'll only grab 16. Well, you only grab 16 when you only have a minimum amount of memory. But you got a half a terabyte of RAM. Don't just grab me 16 dynamically on demand. Go grab me the full allocation as possible of 256 60K slabs of FS buffs. So that's an on-demand thing. A PV buff count is the pool of P buffs per volume group. And there are no standards for how many volumes, HDISC you put in a volume group, and there are no standards for how many logical volumes you put in a volume group, and they're all pooled there. We'll get to that near the bottom. QDEP, well, traditional, we all understand QDEP, I believe. Number command elements.
The key here is
that is at the fiber channel, usually in coordination with VIOS and this LPAR. These are all standard, already well-trod concepts and applications and supports all over these. So I don't intend to address them too deep. What I care to do is to offer content that's new to you. That what I call my value add. Because if I'm not teaching you anything new, I'm not doing anything of any good. But yeah, this is all very well trod practices and concepts that are very well documented in red books and everywhere. Good stuff. Thank you, Tom. But with this a layered approach.
The key tie-in to what Earl was saying earlier about file system I/O, LRUD, finding places to lodge memory, etc. Look on the left side there where it says raw disks. If you're doing a database, which is typically where we see concurrent or direct I/O, and it issues an I/O, it goes down that leftmost pillar there and goes right to the device driver. It skips all of the logical file system code overhead. It skips having to find a buffer in JFS2 or some other type of file system mount point. It skips all of the VMM LRUD overhead necessary to find a page to put the I/O into. And it skips the LVM device drivers, the handoff between LVM and the actual device driver, think HDISC and multipath. That's why we really encourage, if you can do direct or concurrent I/O, do it. You skip all of that overhead. If you can't, if the application can't do it, then we need to do all that tuning in the middle there so that the data flows efficiently. And that's what the numbers are, a lot of what you saw Earl going through. That's why I wanted to point this out, because it shows in a picture why we keep encouraging the use of more modern versions of the software, in this case databases, because we can skip a lot of overhead and make these applications run much, much better by doing so. It also then frees up a lot of that memory, but the application can use it. We don't need to store all those GFS2 file pages in memory while we're doing the I/O. So it's a really good benefit. So that's why I wanted to show this.
Yes, but there's a lot of inconvenience in dealing with RAW. It works great. And some applications don't allow RAW anymore. What's up? Skipping all.
So with that, I think we can, unless there's other questions or comments on this, we can turn the control back over to Earl.
Thank you, Tom.
Yep.
I'll have wait for Joe. Thank you, Joe. Let me see if I can bring up the right thing. Hey, I did it. That original question from Joe about clonedness, I hope I answered that right. If not, or sufficiently, it's not a matter of high or low or bad. It's a matter of how lucky you are with what you're running, right? Because every workload will differ. Okay, second most important, next most critical memory performance indicator is free frame weights. This is a request for free memory, and there was no free memory in that memory pool. What? You might find that you have 7 digits of free memory, which is a standard for free memory for everybody. At 100 gigabytes of RAM, you should have a low range of 7 digits of free memory, and you'll still get these free frame weights, and you're going to go, why? I see 7 digits of free memory, Earl. Why am I seeing free frame weights? Well, not all memory pools have exactly the same content. One memory pool may run out of free memory, and that's the one doing all the LRUD. So it's on a per memory pool basis. If your memory pool doesn't have free memory and you're trying to use that memory pool, it's got to go make free memory for that memory pool. That's why I've written this. Each free frame weight is a request for free memory in its given memory pool. If your memory pools get out of balance, oops, time to consider a reboot. Now, it's rare today. It used to be a real problem, okay, but we've gotten better with making and keeping our memory pools about the same, but it wasn't always the case. And thus, that request for free memory has to wait for LRUD to scan and free it, the free memory for that memory pool. Free frame weights means waiting for LRUD to free memory from LRUable pages, okay? It shows the intensity of demand for free memory. If your LPAR is using a concurrent I/O, you skip all of this noise. This LPAR, less than 2 days, you used to have extremely high free frame weights. So I had to configure them to address that. And that's my area of tactical remedies. But noticing you've got 9 digits of free free frame weights at 10 days means you don't got enough memory. It's got a real problem, all right? So we have a rule. Let's get to that rule. There it is. 5 digits in 90 days, acceptable. 6 digits, oops. 9 digits at 10 days, which is very typical. It's helter-skelter. We've got a real issue. Yet everything still runs. We just don't know why, okay? So exponentially increases with each digit beyond 5 digits, all right? This subset is rarely ever considered, which is why it's here, why I address it. Start IOs. Roundabout sum of page ins and page outs. These are all the IOs that are started. and is usually somewhat the sum of page ins plus page outs, okay? So I have not seen it break from that. These are your default JFS2 IOs, not concurrent IO, raw ASM, GPFS, all right? Start IOs. The count of default or RBR or RBW IOs going through the traditional stack. Requests reads from storage through free memory into the cache, transfers writes from the processes through free memory into the cache. Okay, so those are all the IOs started. If you're using default method RBR, RBW, we have what's called coalescence. JFS2 automatically takes sequential reads and combines them into fewer IOPS, fewer larger read requests to of SAN storage, as well as sequential write requests. They coalesce into fewer IOPS for efficiency. This sequential IO coalescence is wonderful. But you don't get this when you do concurrent IO. Probably you get it with GPFS, and raw doesn't do this, right? I mean, so this is a feature of JFS2 at default RBR, RBW. Only sequential IOs coalesce. Random IOs don't. Here's the reason why I bring this up. You start that many IOs, look how many you get done. What? If you start a lot and you get fewer done, the reason why you get fewer done is they are reduced by sequential IO coalescence. The greatest ratio I typically see is a 300-to-1 ratio, meaning you've got extreme sequential IO that are coalescing many IOPS into fewer. I don't get to see those chat requests for very long, okay? So I'll rely on Joe. So this is the coalescence ratio. Here, given that that's a 21-to-4 overall significance ratio, is telling me that this workload is mostly doing random IOs. They're not doing massive data warehouse sequential IO reads and writes, okay? So it's a character of IO. But the IO dones is after reduction by coalescence. If you're a concurrent IO world, you betcha that's probably root VG and any other minor JFS2 that is not concurrent IO. Okay? So you start the IOs and IO dones are coalesced. That's why they're a smaller number. Now this is background for where I'm going. Where I'm going is pending IO waits. Now this is part of normal AIX function. A pending IO wait is when an IO down is launched, or whatever that IO is doing, and of course the kernel follows up on all of the IOs. It follows up to make sure they're completed successfully. It waits a little while, I don't know how long, and it goes and checks, is this IO done, and is it complete? Do I have an error? Did it, and if it checks that IO for completion and finds that IO is still pending, that means it's still running, it needs to check again. So as you see here, of the 47, whatever the rest of the IOs that you do, a proportion of them are pending, meaning they took a little longer. Now, it could be slow storage, and that's traditionally what we expected, and it could still be today, but it's less so today. We have other things that causes IOs to pend. They eventually all successfully complete. But I use this in my tuning to get a sense of IO responsiveness, not always tied to the speed of your SAN storage, often tied to something else. Pending IO waits, less than IO dones by 2 to 3 digits is normal and expected. It's very typical for direct IO methods are used, okay? Here you see it isn't. Warning, pending IO waits less than IO dones by 1 digit. Start watching it. If they're equal digit count, like you see here, okay, you got a problem. And it's critical if pending IO waits is greater than IO done by 1 digit. Now, I only wrote 1 digit here, but literally last month I had a customer bring me a 2-digit greater than inodes of pending IO waits. And I just went, wow. So I had to go fix that. Here's the problem. It is likely IBM support won't recognize this issue as a problem. Man, that is correct and proper. There's nothing wrong with AIX. It's just the workload you put on it, okay? So if you find this problem, it's still not good for performance. Your workload will run. AIX handles it just fine. But if support won't recognize it as an issue, I step up. You write to me, I'll fix it, unfunded, for free. Because if I'm going to teach you something and support won't handle it or don't recognize it, I will take care of you, okay? It's complicated how to fix this, but we will fix it, all right? By the way, I didn't mention this last presentation in January. I usually work by engagement that's funded. Not by customer funding, most of the time not by customer funding, but by other means of funding. But my manager allows me to give away 2 hours for free for anyone who asks. If you have a concern or a mystery, or you just want to understand what your workload is doing, write to me, especially first quarter of every year, because I got no engagements. And I'll give away 2 hours free, you know, I mean, I can say a lot in 2 hours. I can see a lot in 2 hours. Write to me. I send you my script, or you already have my script, and you run the workload. Harry, you're a wizard. And send me the output. And I schedule up a WebEx, and we go at it. And this is making lab services more accessible to everybody. Okay. How's that for a generous offer from an IBMer? So hopefully you don't have those issues. If you are running concurrent I/O, you will not have this issue. Subset. These are the power events of all processing by this LPAR. These are the numbers of which Power VM gives to your LPAR to do its workload. These numbers are indicative of what your LPAR uses. With decrement interrupts of atomic CPU attention since boot, decrement interrupts is how Power VM gives CPU attention to your logical CPUs. The hypervisor gives CPU time by allocating decrement interrupts to logical CPUs, and decrement interrupts are only ever useful workload, meaning CPU attention to execute user and kernel activities. Otherwise saying decrement interrupts are never used to underlie wait processes. This is only productive CPU. I addressed it in past years. That was a mistake. I may address it going forward, but that number is the definitive number of CPU used. In other words, all context switches, interrupt, system calls, plus anything else, everything else, is executed by decrement interrupts of atomic CPU attention since boot. Everything occurs in that count, and that count is constantly growing second to second. You watch it. It's always growing. You want to look at it now, those who are logged in live? mpstat-I-1, all lowercase. And you'll see the decrement error column and how it goes up and down wildly in every second. These are the power events of only this LPAR. Cumulative counts over days uptime. They are definitive, precisely definitive for CPU usage. Because all decrement interrupts underlie every interrupt, device software, and context switch, and system calls. Okay? Yet no capacity management tool cares to use their precision. This is a fault. Those numbers should be in capacity management because capacity management should be aware of CPU virtualization and all the rest of that technology. I'm getting a sense that the practices of capacity management have not evolved very much through the decades. I could be wrong, I'm not a capacity manager. But I'm getting a sense those practices have remained constant through the decades. Yet, the technology has changed just a little bit through those decades. This is my little rock that I throw at evolving capacity management practices. These numbers need to be included in capacity management. Why? Because our LPARs are getting bigger and bigger and bigger. These numbers matter greater today.
So, you wrapping this up then, Earl? We're
like
close to the end of the hour, I guess. Right? Yeah, you thought you'd end early.
Oh, I thought I'd end early. I was talking too much. I'm sorry. We got the other half to go.
No way.
No, I'm not kidding. It's the other half here. Now, you guys are going to have to read this for yourselves. Or Joe, if he gets skunked on a presenter, he can carry on here. These numbers you can read on your own. -V is very common. People have been using it for years. Get into memory pools here. And I'm going to just leave it with the memory pools. These are memory pools. Memory pools are mapped to the same or different DIM sets. What the hell am I talking about? They're hardware mapped. See that column SRAD number? SRAD DIM set 0 has those memory pools mapped to it. Well, if you only got a little LPAR in one memory pool, or two memory pools on the same SRAD DIM set, or 9, they're all looking at the same DIM set. But as you can see, these 48 memory pools are across all 8 of them. This is why it matters. And SMT8 automatically doubles the number of memory pools. The count of memory pools is accommodated by the count of total logical CPUs. If you go to SMT8 and then you shift down to SMT4, poof, half your memory pools or thereabouts recoalesce. Well, given the speed of our technology, fewer memory pools that are larger works more efficiently than too many memory pools that are all too small. Well, you know, I haven't written much about that, but I need to introduce the concept before I speak of the physiology. Anatomy before physiology. So this here is mapping memory pools and how they're made. This proves you've got 48 memory pools. Your memory is divided across all 48 memory pools. That's the number of pages in gigabytes per memory pool. You see they're all about the same size. And then LRUable pages is distributed across those memory pools. That's how I know that memory pools, how they're constructed. And then, of course, how much memory is free? Well, this LPAR is 55% memory free, as you see by those numbers. So there's a lot of free memory in each. Well, if all the memory pools are about the same size, that's cool, but sometimes you get a memory pool that is too small, and that's the one that's running LRUD all the time, and it's mapped to the hardware. So this is opening a new perspective on tuning. This is what I call power tuning, how your AIX LPAR manifests on the hardware, and that is missing in most of performance tuning practice. Okay? So read this on your own, guys. This is, you don't need me to comment on. The real depth of the content is that first half, okay? And now I come down to this pretty self-explanatory if I've written it well enough. Maybe I have too much confidence in what I'm saying, but I'm still doing my best, okay? And come down here to the end, and we talk about, I'm looking for a picture of Jon Snow. Here, At the end of this document, you'll see my rules, 1, 2, 3, 4, okay, and, you know, my stepping up here, and other rules, okay? So this will help you note a problem and what to do about it. Here's the one that's the stickiest. FS-puff exhaustion. Sorry, Joe, I'm overrunning a few minutes, but this one is immediately useful to everybody. Very stubborn to tune these. You exhaust these all the time. Originally, the scale of AIX was founded on the assumption that no file system was greater than 2 gigabytes. Now, I asked the Powerverse, how many 2 gigabyte file systems do you have? None. They're all much more than 2 gigabytes. So these are pretty stubborn. And this is from having too few file systems that have too much data in them. If you have too few file systems with a lot of data, it is very easy to have I/O intensity that is too great, too long through one set of FS buffs. FS buffs are dedicated per file system. We have thrown tactics to reduce these. These issues do not occur for concurrent I/O issues, concurrent I/O implementations. But if you have this very stubborn thing here, the real solution is to provide too few file systems that are too big with too much data into many smaller file systems to spread that intensity across the FS buff dedicated allocation of each and many more smaller JFS2 file systems. That's the real way to do it. And fortunately, it's structural. Dang it, I thought I would have too much time. Look what I did. I'm sorry, Joe. To you, Joe.
Cyril, so I think, you know, it's just so much information there to cover. I think Tom had some things he wanted to talk about before we wrap completely up.
Yeah, so Tom here, I know we're late on time, but Earl, there's a fair number of questions showing up in the Q&A, and I think it'd be good if we went back to a quick review of what do those free frame weight numbers mean in terms of, oh, I see 10 digits, or I see 12 digits. What should I do? Where should I look? And a similar one with, I'm getting, you know, big numbers of I/O weight digits in a certain time period. So the rules of thumb, what do they mean? What do I want to look at next if I see a big number?
Okay. I/O weights are idle CPUs while there are I/Os on the P&W run queue. Oh, gosh. Sorry, that's the alarm for old man to take his pills. I/O weights, the CPU WA column is about CPU idle time while their I/Os are on the run queue. It may be because of slow I/O. It may be because of something else. I know locking. Reference for understanding that number is if your single digits CPU WA, you're fine. Everything's great. Your storage is very responsive. But if you're double digit sustained, you're not on solid state storage, you're not on flash, you have CPU idle time while their I/Os are on the run queue. It's my other presentation. If you're double digit sustained on SSD flash technology, reach to me. You've got something profoundly out of whack. If you're double digit sustained WA column CPU and you're on spinning disk, well, that's kind of your life, okay? Because that's what it has always been. So what does it mean? Well, you don't got any particular problem. You may have too few file systems with too few files that are too big. In a 2/10 I/O in this case. And you overwhelm the FS blocks, and it causes your I/Os on the run queue to live longer. And, you know, there are tactics for that.
with Tom here. I've spent pretty much a career delving into where is the I/O slow. It takes experience, and it takes a bit of sleuthing sometimes. There are easy ones to surface, and then there are some that you really have to dig deep to find out where is this thing really slowing down. Relative to processor speeds, memory speeds, etc., you know, an I/O is an eternity, you know, a millisecond compared to how fast the threads run in the system. It's like since the dawn of time for just a few milliseconds for an I/O. So it's not something you can answer just in, oh, I see pending I/O weights at this scale. Here's where the problem is. As you saw with that I/O stack that chart that I showed, there's lots of places just in the system that it can go bad. And then once it leaves the wire or leaves the system out the port and it's out on the quote wire, you know, I know it's glass, but there's lots of things out there that you have virtually no control over with modern SAN fabrics, switches, arrays, etc. So where's the problem? That's an investigation. Lots of I/O weights say that there could be a problem there that you should go look into. Talk a bit, Earl, about the 8 digits or 12 digits of free frame weights, etc. And because I'm getting questions here in the chat like, oh, I have 8-digit free frame weights and we have 36 terabytes of RAM. What do we need to tune? Or
okay, I'll jump to that.
You know,
what you do is you increase
10 digits of.
Yeah. What I do is I try to preclude when when a memory pool gets empty of memory. Okay, empty of free memory. And so what I do is we increase VMO, min free, and VMO max free from default 1088 and 960. First jump, if you got this problem, is you're going to still run LRUD like crazy, but you don't want any given memory pool to hit 0, because when it hits 0, that's when the free frame weights occur. So what I do is I raise min free and max free first jump to 12 capital K and 10 capital K. Max free equals 12K and min free equals 10K versus 1088 and 960 of 4K pages. We're moving it up to 12K and 10K. Now, that will help. Won't solve everything. And if it's a problem, open up a PMR. If they don't tell you how to fix it, or they say, everything's running fine, then reach to me. I'll tune you through. I mean, if you trust me, then I'll tune you through and get it running. Free frame weights is actually a symptom of the defaults of AIX. AIX must set its defaults to the minimum amount of memory the LPAR is required to boot with. And so defaults are set to the minimum amount of memory. Well, if you've got minimum memory is 4 gigabytes, I think, and you're booting a 400 gigabyte RAM LPAR, well, you're still running with the defaults, assuming 4 gigabytes of RAM. It just can't be helped. What I do for tuning is I adapt the scale and technology parameters governing AIX to the reality of the capability of the hardware. That's what tuning is supposed to be, isn't it? I might have said that too fast. VMO, min free, and max free. Bump them up, 10K, 12K.
And support usually has some pretty good recommendations for where to start with bumping those up based upon what a perf PMR shows them.
Oh, they do. That's good. I didn't know that they start doing that.
So, Earl, when you go through the numbers and you say, well, I've never seen one bigger than this or like this, et cetera, inevitably someone's going to post a challenge in the chat. So I'm going to read you, not the actual number, but one of our people in the Powerverse posted a little snippet, and he said he's got a 12-digit translation fault and a 10-digit page ins over 58 days.
Sure sounds like he's using current IO to me. That's a nice workload.
So we can't tell you what is happening just from that number, but there's probably some opportunities to inspect that a little bit and see where might things be opportunities to improve, or at least just understand what's going on, and maybe things are fine. Okay.
Yeah, you guys, if you're worried, if you're concerned or you're curious, take my script, run it, send me the goodie, send me the text file, and if I see anything like critically urgent, I'll even call you directly, because it doesn't take me long to find things. I mean, finding a problem, I spend less time doing that than yelling about it, okay? It's kind of sick. But that's all that I do. I don't do anything else.
So I should probably put your latest script up on the wiki then, right, Earl?
You already did, Tom. I mean, Joe, you already did. It's already up. Thank you.
Oh, that was in the stuff that you shared before. Okay. All right.
Yep.
Okay, so it would be in the January, on the wiki, it would be in the January session, everyone. Okay, well, I think we should probably wrap up then. Since Earl finished early today, and he said he was going to do that.
I didn't finish early.
Earl, thanks so much. This is, I mean, obviously great stuff. Lots of good questions, and you know, a lot of interest in it, just as evidenced by all the people that hung around to pass the time. So thanks so much, Tom. Thanks for all the insight that you're providing as well. Really appreciate it. And I guess we'll definitely get Earl back. He's doing all new sessions for 2021, so we'll have to get him back later in the year. As I said, next month we're going to talk about AIX and what's happening there, new stuff and all that with 7.3. All right. So with that, again, thanks, Earl. Thanks, Tom. And everybody have a good month.
Goodbye, all.
Bye-bye.